Welcome to the Science Podcast for February 15th, 2019. I'm Sarah Crespi. In this week's show, I'm talking to staff writer Paul Voosen about whether there's a hard limit on weather prediction. Is 15 days as far out as we can get? And Meagan Cantwell and Trygve Fossum discuss his paper on an autonomous bot that's mapping phytoplankton off the coast of Norway. How far out can we predict the weather? We've gotten pretty good at it, but is there a limit? Staff writer Paul Voosen is here to discuss a study that says, about 2 weeks. That's the maximum for the mid-latitudes anyway. Hi, Paul.
Hello.
So the app on my phone gives me 10 days of weather, and it's pretty good. I expect a little variation in those latter days, but is that the best that we can do right now?
It is the best we can do right now. The top-end models from Europe and the US, really, they max out at skillful predictions at about 10 days.
We've been getting better at this over the last few decades. What has been that rate of increase?
Each decade, they've added one additional day of predictability. This is a really great success.
But is that going to stop? We can't just keep adding one day of prediction a decade forever?
Probably not. It would be nice. It'd be great for job security for forecasters.
Yeah.
But this is something meteorologists have wondered about for 50 years. And they've often said, maybe it's about 2 weeks. And this newest study seems to say, it does seem to be about 2 weeks.
How can a study prove a negative, that we can't get better than, a certain limit?
It can't, to a certain extent. There's always going to be ways you could improve this method. But so they took the latest version of the European model, which is considered to be the best in the world, and ran it about 120 times, which is really operationally expensive. These are supercomputer type models.
So they ran it 120 times. Did they change something about the initial conditions or what they were measuring or what they were excluding in these different sessions?
Mm-hmm. Yeah. So, a lot of the error that we see in models could also derive from our uncertainty about what we're observing today. Right. So we don't have these perfect understanding of the weather. And so trying to tease out what is a problem due to our imperfect knowledge versus the inherent chaos of the atmosphere has always been an issue. But if you do this kind of big ensemble suite of models, running them all together, you can artificially make it seem like you have no error in the observations. You can narrow the range, reduce it to 10% from the current uncertainty. And that creates this kind of artificial certainty.
This is kind of presuming that we're even better in the future at measuring, that we know more about how weather works, and that we're better at inputting that data into these models. And when all those assumptions, we still get this 2-week limit.
Yeah, we're implausibly better. We'll probably never get that good. And it comes to this 2-week limit that Edward Lorenz, who is a famous meteorologist and mathematician, father of chaos theory.
Mr. Butterfly.
Mr. Butterfly, in fact, he postulated in a 1969 study that probably seemed to be about 2 weeks. A lot of people quibbled about the model, said maybe it didn't, really look like the atmosphere. But now these new models that do look a lot like the atmosphere to the point of even having convection, the kind of cloud thunderstorm systems forming in them, which hasn't been the case in the past, still run into chaos after 2 weeks and are no better than you or me guessing based off climate records.
Let's go back to the butterfly effect. Great move, not a great move. But for people who don't know what this paper was about, I was kind of surprised that there was a paper. I kind of just thought it was like a thing that people say from sci-fi.
It was that too.
That's the crushed butterfly.
Yeah, it's the crushed
affecting
butterfly.
History. This is the flap of a butterfly's wings affecting weather.
Yes. Yeah. So Lorenz kind of seized on this zeitgeist, I think, too. The paper is from 1969. I think he coined it in the early 70s on referring to this. But it's something profound. It's not just about this dependence on initial conditions, but it shows that when you have these nested, chaotic systems, that it's just impossible to predict beyond a certain limit because this error starts at these very small scales and then infects each level up and up and up until it's destroyed the whole system. This is something, even if you have perfect knowledge of initial conditions, that can't be helped.
Wait, so if you have perfect knowledge of the initial conditions, you still can't know because the math is too hard?
I don't know because no math can help you.
Okay, so that really does put a hard limit on what we can know about the future of weather.
Probably.
What about these long-term predictions where they say this is going to be a hot summer or a snowy winter? How does that fit in with this finding?
That's a different kind of forecasting. This is more about the day-to-day kind of weather forecast. Those are called subseasonal to seasonal prediction, and they use seasonal patterns on things called like the Madden-Julian oscillation, these things that can govern. You can't make this, oh, it will rain 6 months from now in X place, but you can make this kind of broader prediction. Oh, it might be rainier than a normal month. And that's a very active area of research and promising.
So looking at broader patterns to be able to make broader predictions, but not sinking into like July 14th and just telling you that's your sunny day that you should get married on.
Yeah, the seasonal prediction, there's really the merit of weather research and climate science.
So speaking of climate science, how does climate change affect our ability to predict the weather? If we're trying to do these day-to-day predictions, are these models going to hold up if a lot of things change about the planet?
The chaotic short-term weather, I don't think it will. These models are initialized with the data every 6 hours or 12 hours. And so they, that represents the world as it is right then. And that's just a quick snapshot. And then you're just projecting these atmospheric flows out from it. So it doesn't necessarily depend on climate knowledge.
It's just the weather processes, those are the same. And we just look at initial conditions and get our prediction.
Yeah.
But maybe these broader oscillations where you're looking for seasonal changes, those might obviously be more difficult to understand under climate change.
Yeah, they might be more difficult, or they might be just more challenging. It's not predicting a static world, it's a changing world. So you're trying to it just makes it a little trickier, I would say. But that's why this field is really coming from climate science as well, that people are already trying to understand this. And they were trying to understand it for 20 years from now, and it started to be 10 years from now. And now it's moving into these seasonal predictions.
We talked a little bit about the benefits of knowing the weather in advance.
Mm-hmm.
Hitting this 2-week limit, is that going to make for a big improvement in some of these things that people rely on knowing the weather for?
I think every day you add is a huge gain for the economy, especially people who really depend on knowing. I'm sure there's an infinite amount of money in Wall Street interested in this. Airlines, farmers, all the people that really just depend on this will be a great boon for them.
Like that example you gave of someone getting notification that there'd be snow on their flight.
Yeah, the lead scientist on this study, as he was finalizing the study, he got a notification that his flight to London was going to be problematic 5 days out and that he should rebook it for free with the airline. And he was like, well, I should listen to the weather forecasters, given he is one. And he took the early flight, had a lovely day in London, and then his flight was canceled, the original.
All right. Well, thank you so much, Paul.
Yeah, thank you.
Paul Voosen is a staff writer for Science. You can find a link to his article and the research we talked about at sciencemag.org/podcast. Stay tuned for Meagan Cantwell's interview with Trygve Fossum on using autonomous robots to map phytoplankton patches off the coast of Norway.
Phytoplankton, microscopic plants of plankton, play a vital role in the productivity of ecosystems, but characterizing exactly where they are in the ocean is challenging. I'm here with Trygve Fossum to talk about how he and his team created a 3D model of where these phytoplankton occur using an automated underwater vehicle. How are you doing?
Good.
So your study was conducted in Norway. What brought your team to this specific study site?
We did this study at an island called Runde. At this island, there has been a famous bird mountain that is home to a number of different seabirds that forage on different fish in the ocean outside. However, during the last decades, there has been a sharp decline in the number of birds. To better try and understand what is happening, we try to collect data across the whole ecosystem around this island.
Phytoplankton are at the base of this food chain. So in order to characterize exactly where these phytoplankton are, before going into your methods to evaluate this, what was traditionally done to do a survey like this?
Traditionally, it has been done from boats, ships, by deploying instruments overboard, either pulling them straight up and straight down and looking what you have, or actually in some cases towing them behind a ship.
What were the limitations to those kind of methods?
Ships are still the most important sensing platform in oceanography, but it's limited in sampling on a sparse scales. It cannot do detailed surveys of the water column. It cannot maybe move that fast. and their mobility is limited. So ships are important, but they're not covering the process. We want to study at a scale which is good enough for definite representations.
Phytoplankton are also not consistent in where they are. The concentration varies a lot. How does the distribution of the phytoplankton usually impact the ecology of an area?
We usually call this patchiness, and it relates to a number of biophysical processes, biochemical processes in the water column in different ways, on different scales. And it's a very hard question, and there are a lot of people trying to understand these intricate mechanisms. Our paper tried to map these out in a way so that we have a measure on how patchy and how this distribution actually is.
To get a better sense of the 3D distribution of these phytoplankton, your team used an autonomous underwater vehicle, or an AUV, to characterize exactly where these phytoplankton are. How did the AUV survey this area to create a model?
What we have developed is a system that allows the AUV to take decisions based on the observation it does during the mission. So this way we're utilizing all the information that is available to us. In the beginning, it's actually boxing in a volume of water, so it follows on the sides of a volume, and based on what it sees when it's traveling along the sides of this box, it estimates how the distribution of phytoplankton is inside. The robot tries to optimize its route through a given volume of water, trying to give the best map of the amount and distribution of phytoplankton, and it does that by utilizing a statistical model that it builds during its journey through the water, and it continuously updates this, and the subsequent data collection is planned based on this estimate that gradually gets better, and then the sensing strategy also gets better.
What kind of sensors are on this AUV, and how does that specifically help you measure the amount of phytoplankton in the water column?
Phytoplankton is usually measured as a proxy through chlorophyll. So by measuring the presence of chlorophyll, we're actually trying to get a bulk measurement of how much phytoplankton there is. We use statistical framework called the Gaussian processes to try to do this in an effective manner so that we can take this measurement of chlorophyll and tie it to a concentration model, plan our data collection. So the AUV tries to stay in the region where it has the most concentration. It's actually interesting to get the map of the highest concentration, because you can usually tie this to other types of measurements, which we have done in the paper.
How big was the area that you characterized, and how long did it take for the AUV to generate a 3D model of the area?
It's 700 by 700 meters, and the AUV uses 40 minutes approximately to cover the sides of the box. And once that model is made and we have an estimate, it uses 40 minutes to traverse the insides of the volume. The whole thing takes approximately 1.5 hours.
Oh, wow. That's really fast.
Yeah, and it needs to be fast because, as I said, there's current. So if we spend too much time, we don't get the snapshot. We only get some smeared out snapshot that is actually very time dependent.
Were you able to get other measurements besides chlorophyll from this 1.5-hour traverse?
So it augments the other measurements. So you can say something about, is the concentration based on a salinity layer? Are the phytoplankton distributed along this gradient of temperature, salinity, or whatever? Or is there some other physical effect that is keeping them where they are? And then you can look also at the interaction with the zooplankton, which is measured from the boat. In our case, we had something called a silhouette camera, which measures and counts the number of different zooplankton species so that you can see how this distribution is affecting the phytoplankton. Because if the zooplankton is eating the phytoplankton, you will have a low concentration. But this concentration can also be because there is a physical force in the ocean at this point, or a current or something else. And in order to make claims about that, you need to know how these things are related. essentially need more than one data set in order to be sure that your statement is actually correct.
Based on this survey, did you find any sort of relationship between these other factors and the presence of phytoplankton?
So this paper was basically, it was more methodology focused. They're still looking at the data for this one because, we have so much data and there's so many
right.
small things to do.
So I guess the mystery of why the birds are declining is still not solved then.
Yeah, it's essentially a picture that you need to build over time when trying to find out something about the birds, because we took a snapshot of that area and then that tells us something about the state of that ecosystem at that time. And in order to say something about why the birds are declining, we need to go back and take that snapshot once again and then really go detailed into what changes are we seeing from snapshot A to snapshot B.
Thank you so much.
Sure. Pleasure to be here.
Trygve Fossum is a researcher at the Applied Underwater Robotic Laboratory in Norway. You can find a link to his research article at sciencemag.org/podcasts.
And that concludes this edition of the Science Podcast. If you have any comments or suggestions for the show, write to us at sciencepodcast@aaas.org. You can subscribe to the show anywhere you get your podcast, or you can listen on the Science website. That's sciencemag.org/podcasts. To place an ad on the podcast, contact midroll.com. This show is produced by Sarah Crespi and Meagan Cantwell and edited by Podigy. Jeffrey Cook composed the music. On behalf of Science Magazine and its publisher, AAAS, thanks for joining us.